So before we talk about other methods in detecting extrasolar planets, I've got a couple of questions. Here is our second question. What will have the largest Doppler shift? A, something that is fast moving, B, something that is slow moving, C, something moving away from us, or D, something moving toward us? Go ahead and think about it and we'll discuss in just a bit. All right, so when we're dealing with Doppler shift, this is relative motion, so whether things are moving towards each other or away. We've talked previously that when objects are going away, the wavelengths stretch out, and if it's coming towards, the wavelengths shrink. Okay, but that's wavelength. That has nothing to do with the amount of shift. What determines how much the wavelength is stretched or squeezed is speed. The faster an object is going, the greater the shift of the wavelength is going to be. Okay, so when we first talked about this, we used the example of a race car. Okay, so in a car race, the cars are going 100 miles an hour, and when they zip past, you can really hear that change in pitch because of how fast it's going. But when we compare that to a car that's just slowly rolling down the road in front of us, we don't hear the change, and that's because it's going really, really slowly. Okay, so a large Doppler shift means the object has to be moving very, very fast, so it is A. Something that is fast moving will have the greatest Doppler shift. Here is our third question. Which planets move the fastest? A, planets close to the star, B, planets far from the star, C, large planets, or D, small planets. Go ahead and think about it and we'll discuss in just a bit. All right, so this goes back to Kepler's laws. So according to Kepler's laws, specifically the third law, planets that are in move fast and planets that are far away move slow. So the closer it is to the sun, the faster it goes. The farther from the sun, the slower it goes. So in this case, it would be A, planets that are close to the star will be the ones moving the fastest. So our second indirect way of detecting other planets is by using the Doppler shift, but not of the planet, of the star. So the idea is that, again, the star is going to wobble. And as the planet pulls on it, sometimes it'll be moving towards us and sometimes it'll be moving away. If it's moving towards, it'll blue shift. If it's moving away, it'll red shift. So we can look for this back and forth blue shift, red shift motion of the star. And if it keeps happening over and over and over, then we can pretty well tell that there's going to be a planet there. So current techniques using this Doppler shift to figure out planets are there can actually measure motions as small as 1 meter per second. Hey, that is the same as walking speed. In fact, it's actually a little bit slower than normal walking speed. So this method is again going to be sensitive to stars that are going to be moving very quickly. That also means that the planet is going to be moving very quickly. So this is going to be sensitive to planets that are very close to their star. However, because we have the star getting pulled around, we also want to have a very strong gravitational pull. So this is going to be sensitive to large planets close to their star. Now, if you remember, when discussing our own solar system, where do we expect large planets to be? Close to the star or far from the star? Yeah, we expect them to be far if we're using our own solar system as the example. Unfortunately, the universe loves to make fun of us. So the very first extrasolar planet ever discovered around a sun-like star, so specifically main sequence, was done using the Doppler shift method. This was around the star 51 Pegasi, so it's in the constellation Pegasus, and it was found with a 4-day orbital period, meaning that it circles completely around its star in just 4 days. So that sounds pretty awesome. The only problem is that it was a planet larger than Jupiter. So we have this Jovian planet, but it's super close into its star. We're going to have to talk about this more in detail later. Our third method in detecting extrasolar planets is the transit method. A transit is where an object, in this case a planet, is going to cross in front of the star. From our point of view here on the Earth, we actually see occasional transits of Venus and Mercury. Because they're inferior, they're closer to the Sun, they can actually go between the Sun and us, so we occasionally see Venus or Mercury cross in front of the Sun. Well, the idea is that when this happens, the planet is actually going to block some of the star's light. So in this case, what we're looking at is called a light curve. Up and down, we have the total brightness of the star as seen by us, and then along the bottom, we're looking at time. So it starts out and the star is full bright, then we have the planet cross in front, and it blocks some of the light until the planet's done crossing through, and then the star comes back up to full brightness. Okay, so we look for this dip in light as the planet is crossing through. That is a transit. Now, it may also be possible to see an eclipse. So in this case, the eclipse is where the planet goes behind the star. Now, if you remember, a planet's reflected starlight is going to be really, really small compared to the actual brightness of a star, but we might be able to detect a faint dip, especially if we're looking in the infrared and the planet is really, really hot. Okay, we'll talk a little bit more about that later. The Kepler mission, which was launched in 2009 and actually ended just last year in 2018, 2 years ago in 2018. The Kepler mission, which launched in 2009 and ended just a couple years ago in 2018, its entire purpose was to use the transit method to search for extrasolar planets. It was designed to measure the 0.008% decline in brightness as an Earth-sized planet went in front of a Sun-like star when the planet was around the same distance as the Earth is from the Sun. In other words, it was built to try to find other Earths. Now, over its run, it found over 2,500 confirmed extrasolar planets. So we've had other detections of them. We know for certain they are there in over 440 star systems, and another 5,000 candidates. So these are ones that could be, but they might be the star dimming for other reasons. We need to have follow-up observations to find out if that's what's actually happening. More recently, about the same time that Kepler ended, we had the launch of the TESS mission, which was the follow-up. It's also using the transit, and it's also expected to find lots and lots of extrasolar planets. Now, there are a couple of other ways that we have found extrasolar planets, but these are not the main methods. The main methods we've used so far are the astrometric, the Doppler shift, and the transit. Hey, these are the big three. These are what have found the very most. The transit method has by far found the most. Then second is the Doppler shift, and astrometric has found quite a few, but not nearly as much as the other two. We're going to talk about a couple of other ways we've actually found extrasolar planets, but these are uncommon. Okay, so another way we've found extrasolar planets is through microlensing. The idea of the microlensing is the bending of light due to a massive object. Okay, it's what we've referred to previously as gravitational lensing. So the idea is that we see some distant star that we're keeping track of. If another star crosses between us and the distant star, then this in-between star is going to lens the light onto the Earth, so the distant star is going to become brighter. Then, if this lensing star in between also has a planet, when the planet gets into the right orientation, a little bit more starlight focuses, so the distant star becomes slightly brighter again. Okay, so we have this very telltale way of the distant star becoming brighter through gravitational lensing, and that will reveal the presence of an extrasolar planet. Now, in my opinion, one of the most exciting things that has been happening recently is actual imaging, actually taking a picture of the planet. Hey, this is going to be a direct way of finding the planet. Now, this is going to be best done in the infrared, because in the infrared, if the planet is hot, it will actually be giving off its own light. Not as much as the star, but more than the small amount of reflected light. So in the infrared, we can actually see the planet. So here's the star, and that's the planet. So hopefully we're going to get a lot better with this technique and actually start imaging the planets themselves, which would be really cool.